Hi, in this video I'm just trying to give a very basic idea of modal logic. What are the fundamentals, and all these would be related to the system K. I won't be entering any new system, so at the end of the video you should be able to solve some of the basic problems using the truth tree method. So let's begin by what's modal logic. Uh, Modal logic basically deals with the expressions of possibly and necessarily. So, to denote these expressions in logic, two new symbols are introduced, possibly using a diamond and necessarily using a square. Necessarily A, it means that A is certain in some world. Remember, we use worlds in modal logic. So A is certain. If you are saying in world 0, then in world 0 A is certain. Possibly, on the other hand, means that A is possible, but the implication is far reaching here. Possibly A means A will happen in some other world. So like if we say that it might rain today, it means that in some world it's raining today. Okay, so these two expressions are very similar to uh, quantifiers in our propositional and predicate logic. uh, just a second. This is modal predicate. Okay, in modal we have square, here we had x, diamond, and some x. Remember that a statement like ghosts exist, we used to translate it into some x and gx. It means that there is at least one x which is a ghost. So some x, or this is also called existential quantifier, asserts that there is an existence of said being, whereas in x or a universal statement it just says that if there is an x, there is always a conditional statement. So if there is an x, let's say px, then so and so. If, it doesn't necessarily say that x exists, but in a particular statement, or when you use an existential quantifier, it means, it asserts that there is at least one x. Okay, yeah, this can be wrong, this can be false. Similarly, in modal logic, square is very much like a universal statement. It necessitates something, but that doesn't mean it has to happen. A diamond, on the other hand, it says that it is possible, but it means that in some world it is happening or it will happen. Again, we are talking about worlds here, so we must explain why these worlds are being used. Any logical statement in modal logic, on the face of it, in the very beginning, denotes world 0. It can be also said to be the world prime. You can take it as it is the original world, and there are infinite number of other worlds which are the copies of world 0. Okay, so in the beginning, when an expression is given like P implies Q, it means that it's being said about world 0. So whenever we'll be solving a numerical problem, we have to mention in which world the statement is being referred to, and if there are no additional worlds yet, then you have to put 0 after a comma before solving. Then we have two basic rules of negation that is used throughout all the 6 systems. These rules: not square p is equivalent to diamond not p, and not diamond p is equivalent to square not p. Everything else, all the or the other rules of negation would be just derivatives of these two. These are the main two. Like if you say not diamond not p is equivalent to not square not p, sorry, is equivalent to diamond p. So yeah, we have just used this rule to explain this one. Now if you would remember, before solving deductions of predicate logic, the first thing we had to do was remove their quantifiers. For instance, if there was a statement sum x such that px implies qx, we cannot treat this statement as if now. We first have to remove this sum x, and for that we had the rules of instantiations and generalizations. Similarly, here in modal logic, we do not have those instantiations. Instead, we'll be removing squares and diamonds by introduction of new worlds, or at times introduction of the same world again. So to solve a problem, let's say we have an expression not p implies diamond not q, something like this. The first goal is to remove this square and this diamond, okay? But like I've said, to remove these shapes, introduction of a new world is necessary, otherwise you can't do it. And that brings to our next rule: a new world can be introduced only when there is a diamond given. So a diamond p, if it's there, then we can take a diamond p in world 0. So if it's already given, then you can assume 0 relates to 1 or 2 or 3, doesn't matter. It simply means that you can take a new world 1. It's like saying it might rain. This statement right now means that it might rain, just like that, it might rain. So there is a possibility that it might rain in some world. When we say 0 relates to 1, and after that we come to the conclusion p1, these and these gave this. Now it means that it's raining in world 1. So you always need a diamond to be present before introducing a new world. And once you have introduced a new world, like if when 0 relates to 1 is already given and there is a square p0, then these two together will give you p1. So to summarize, diamond p can give you on itself, diamond p0, sorry, that 0 relates to 1, and if there is a square p and there is 0 relates to 1, These two together can give you P1. Okay, you can see the four rules that I have mentioned. Uh, in the last two rules, you can see if the square AI is given, and if it's given that I relates to world J, then you can conclude that A in world J. Similarly, if a diamond AI is given, then from it itself you can assume that I relates to J and then AJ. The most important thing to remember though is that you need a diamond to introduce a new world. Without a diamond, you cannot introduce any new world. Now, just let's understand some other symbols just to know what they mean. That's it, and then we'll be ready to solve our first problem. This or this simply means that it's asking if the following statement implies, or it's just asking in for a practical purpose that is it valid. So if the statement is it means that is this statement valid, okay, and this new symbol that you'd be seeing, it's nothing but conjunction. Or and you already know wedge for or. This is implication. And this is and. We'll be using truth tree method, so these are the only symbols that you need to know. Also there is negation, or just like this, or these are all negations. So we'll take our first problem. Square A and square B implies square A and B. Okay, so we'll be using the truth tree method. So if you remember, the first step was to negate the conclusion. Everything that follows after this sign is what we have to negate in modal logic. So we'll start by negating this whole statement. Step 1, negating. Remember to put world 0 if nothing else is given yet. Okay. In step 2, it will come to square A and square B in 0 and not square A and B in 0. In truth tree method, we write conjunctions one below another. So we have just assumed this to be P and this as Q, and P implies Q is not P wedge Q, and not P wedge Q. Because of this negation, we apply De Morgan and we get this P and not Q. Okay. Till now we had this problem. Square A and square B implies square A and B. We have to negate the whole statement after this symbol, this one. So in step 1 we have just negated the whole statement and we have written world 0, because if nothing is given you have to assume it's happening in world 0. In step 2, because of this negation we get these values. We have assumed this to be P and this Q. P implies Q gives P and not Q because of this negation outside. There are two rules used here. First is the rule of material implication. It's a rule of replacement, and then the De Morgan's. Using first material implication and then De Morgan's gives us P and not Q. And in truth table method we write and or conjunctions one below another. So this is P, this is not Q. The step 3 here is derived from number 2 by using the rule of negation on this square. We get diamond and then not A and B all happening in world 0. Now since we have a diamond, we remember that when we have a diamond we produce a new world, and an introduction of a world is very necessary to remove these shapes of square and diamond. So in step 4 we'll just assume that 0 relates to 1, and this will give us 5 not A B in 1. Step number 5 is coming from number 3 and 4 combined. Again, if we use De Morgan's on step number 5, we'll get not A in 1 or not B in 1. De Morgan states that not A and B can be replaced by not A wedge not B, and in truth tree method we write disjunction or wedge or using by showing these branches. Remember, we still have this value untreated. So now we'll break this square A and square B in world 0 and rewrite it here. In step number 7, square A in 0 and square B in 0. It's alright to write these conjuncts on either side, on this branch or this branch, doesn't matter. You can leave any branch open, that doesn't matter either. So now we have a square A, and we have this rule that 0 relates to 1, and we knew that if we have a square and a relation to a new world is already given, then square can be removed. So we can write A1 because we have square a and in 0, and we have 0 relates to 1, so we can write a in world 1. Okay, now we can see that there is a contradiction. We have a in world 1 here, and we have not a in world 1 here. So the contradiction results in closing of the branch. We cross at the end of the branch to mark that it's been closed. We still have one branch open, this, and we have one item untreated. Now using the similar rule, just a second. The same rule that we used for a1 on square a0 will give us b1 from square b0, because we already have square b0 and we have 0 relates to 1, so we can write b1. Now again we have a contradiction, not b1 and b1, so this branch will also close. Now you have to make sure that all the items in the tree has been treated. Every single item should be used at least once, and if there is a contradiction, if all the branches has been closed and all the items have been treated, then we can say that the statement was valid. So this example in our case is valid. If there was some case like when the branch doesn't close, or you cannot proceed further if there are no further steps and one of the branches is still open or one of the items are still untreated, then the statement would be invalid. I think this much is enough. Remember that all that we did right now, this all comes under system K, named after Sol Kripke. K system is considered to be the weakest of all 6 systems, but it doesn't mean that K has been rejected by rest of the 5. All other 5 are just the extension of the K. They've added 1 or 2 extra rules to make theirs better. There are mainly 4 rules, and in 4 rules of relation to a world, and in K just 1 is used. So there are 4 rules. Symmetry, reflexivity, transitivity, and extendability. This is the only rule that's used in K instead of those 4 basic rules of modal logic, the rules of negation and the rules of introduction of a new world. Other than that, extendability is the only thing that's used. This is for any world 1 you can take world 2. It simply means that you can extend your world. If you have any one world given, you can from there go to another world. Like if you have world 0, you can go to world 1 or world 2, world, and doesn't matter, you can go to any other world from world 0 as long as it fulfills your certain purpose. The rest of the 3 are not in K, and the addition of these new rules to K gives birth to new systems. That's not for the concern for this video. The problem that we solved should be enough to give you an idea about the basic and fundamentals of modal logic. Thanks.